My name is Caleb Springer, and I am talking about the structure of the group of rational points of an abelian variety over a finite field. I'm going to start by giving a taste of my main result, which is about abelian varieties of arbitrary dimension, back up to talk about the elliptic curve case first, really state the main result after that as a part of the generalization, and we'll wrap up with some examples that show what's really going on. So here's the idea. I'm going to take a simple abelian variety such that the endomorphism ring satisfies certain technical conditions, and then we can precisely describe the structure of the group of rational points as a module over this FQ rational endomorphism ring. And this is going to generalize a theorem of Lenstra for elliptic curves. So let's start there with elliptic curves. So I'm going to take an elliptic curve over a finite field and think about the group of rational points. So these are the ways that I can solve this nice equation with elements from my finite field. And I have a point at infinity too. So elliptic curves are smooth, projective, genus 1 curves, which is a really nice geometry. There is an abelian group structure which is given geometrically on this curve, and this point at infinity is the group identity. And this is what makes elliptic curves special, is because they've got this geometry and the abelian group structure happening at the same time. So the kinds of maps that I care about in this case are maps called isogenies, which respect both the group structure and the geometry at the same time. Particularly good isogenies for us to look at are called endomorphisms, which are just isogenies from the elliptic curve back to itself. Key examples are multiplication by an integer, which we have just by the group structure, and the Frobenius endomorphism, which comes from working over a finite field, so that raising to the qth power is actually a group homomorphism. And these are the two key examples to keep in mind. So when I talk about the module structure, I'm talking about the module over end FQE, which is the ring of all endomorphisms which are defined over the finite field. So I have a group of rational points, which is an abelian group, and I have an endomorphism ring, which acts on this group of rational points. So that this together, the group and the ring, gives me a module structure to work with. And I want to describe this module structure in terms of the endomorphism ring alone, just to understand what's going on here algebraically. Before I identify this module structure, we should think about what the ring end FQE actually looks like. So the Frobenius endomorphism, which is the really key player here for us, satisfies this nice polynomial equation with integer coefficients. And I'm going to identify pi with an algebraic integer, which is a root of this polynomial. And we can split into two cases here. If pi is an integer, then this ring is going to be an order in a quaternion algebra over the rational numbers. In the other case, if pi is not an integer, then this end FQE is going to be an order in a quadratic imaginary number field, which is generated by pi. So in both cases we have orders, but they're sitting in slightly different places. So this is what Lenstra's theorem says. If we take an elliptic curve over a finite field with Frobenius pi and endomorphism ring R, then we can split into two cases, just like I did on the last slide. If pi is not an integer, then this group of rational points is isomorphic to R mod R pi to the n minus 1. And it makes sense that pi to the n minus 1 shows up here, because actually this group of rational points is the kernel of this isogeny pi to the n minus 1. Or in other words, it's exactly the group where pi to the n acts like the identity. Now for part B, if pi is an integer, then we can first remember there's an isomorphism of Z modules, which is to say an isomorphism of abelian groups. And this is a classical result, that this group of rational points is going to be actually this product of two groups here. And then the R module structure is going to come from an isomorphism of rings, where I can think of R mod R pi to the n minus 1 as matrices which act on this group. So coefficients of these 2 by 2 matrices is in the same group. So this gives a really nice description of the module structure of these groups of rational points. And actually, as an immediate corollary, which is nice, this shows that the abelian group structure of this group of rational points is determined uniquely by the endomorphism ring. This is a nice perspective that is used for some computational number theory, such as the thesis of Cowell or the work of Galbraith and so on, thinking about elliptic curve, isogeny volcanoes, and things of this kind. So when you hear a theorem about elliptic curves, you can always wonder if the same is true for abelian varieties, because abelian varieties can be viewed as the higher dimensional analog of elliptic curves. So if we ask this question, can we generalize Lenstra's theorem to all abelian varieties over a finite field? Then sadly, if you're reading Lenstra's paper, you can't even get to the end of the paper before you find out the answer is no, because Lenstra showed that his result does not immediately generalize to all principally polarized ordinary abelian varieties. There's something more complicated going on with abelian varieties, so the whole group of this principally polarized ordinary abelian varieties, it won't work. But still, I want a generalization that is true, assuming some conditions that are automatic for elliptic curves. So just like before, what does the endomorphism ring look like? That's a good place to start. So if you have a simple abelian variety over a finite field of dimension G, then again I'm going to identify the Frobenius endomorphism with an algebraic integer. Then this endomorphism ring is going to be an order in a division algebra, and the center of this division algebra is the number field generated by pi. So this division algebra D might coincide with Q pi, and it might be bigger. And the way to tell how big it is determined by this integer D, so that 2G is D times the degree of Q pi over Q. And you'll notice by looking at these equations that the case of D equals 1 is exactly the case where capital D is equal to Q pi. So this is going to be the commutative case for our endomorphism ring when pi generates a number field of degree 2G. With this in mind, here's a way to generalize Lenstra's theorem. If we fix a dimension and we look at a simple abelian variety over a finite field of that dimension with Frobenius pi, endomorphism ring R, and center Z, then in the commutative case, which is to say when the number field Q pi has degree 2G over Q, and if R is a Gorenstein ring, which is a nice commutative algebra property, then the group of rational points as a module over R is isomorphic to R mod R pi to the n minus 1, which looks just the same as Lenstra's theorem. And in part B, if this ideal pi to the n minus 1 is a product of invertible prime ideals in the center, then we can first describe the structure as a module over the center as the group of rational points is isomorphic to a vector where the coordinates are in z mod z pi to the n minus 1. And this D is the 2G over Q pi over Q, which you saw in the last slide. And then the R module structure, like before in Lenstra's theorem, comes from an isomorphism of rings, where we can think of R mod R pi to the n minus 1 as a ring of matrices that are acting on these vectors that we got in the isomorphism of modules over the center above. So this describes, in these nice cases of the endomorphism ring, exactly what is going on for the module structure of these groups of rational points, just like in Lenstra's theorem for elliptic curves, although we did have to throw in those extra technical conditions. Now let's talk about some examples. So here's a reminder of part A of the theorem. Then some Gorenstein endomorphism rings. For example, every order in a quadratic field is Gorenstein. So in particular, if we have an elliptic curve over a finite field, such that the Frobenius is not an integer, then we know for sure that this commutative endomorphism ring NFQE is Gorenstein. This recovers part A of Lenstra's theorem, where the Gorenstein property was hiding but present. More generally, the ring of integers of a number field is always going to be Gorenstein, although we don't know for sure that a non-maximal order would also be Gorenstein. That's only sometimes true. But more generally, even so, it is sufficient to say that the order has maximal real multiplication. So that would be an order, even though it is not maximal itself, it contains the ring of integers of the totally real subfield that sits below it. And then on the other end of the spectrum, just like we could say something about maximal endomorphism rings, where that's the ring of integers, can also say that in the minimal case, we also have a Gorenstein ring. And the minimal case will be the endomorphism ring Z pi pi bar. In the non-commutative case, here's a reminder of that part of the theorem. We have invertible prime ideals. So remember that if my ring Z is a maximal order, then all primes are invertible. What I mean by invertible is if you can find another ideal so that the product of your two ideals is principal. This is always true for maximal orders, and then you're going to have some trouble as the order gets smaller. But just going with thinking about maximal orders, we can still get some mileage out of this part of the theorem. So for example, if you think about a supersingular elliptic curve where all its endomorphisms are defined over FQ, this is the case where pi is an integer, then this endomorphism ring is an order in a quaternion algebra with center Z. Of course, every ideal in Z is principal already, so they're certainly invertible, and this is going to recover part B of Lenstra's theorem. And a little bit more generally, if I think of pi being plus or minus the square root of a prime, p, where p is not 1 mod 4, then the center of my endomorphism ring is the maximal order z adjoin the square root of p for any abelian variety in the isogeny class corresponding to pi. And here I'm implicitly using the Honda-Tate theorem that says I can just specify a VQ integer, which is to say the integer I associate to pi, and there are some abelian varieties associated to it. And this is a two-dimensional example with a non-commutative endomorphism ring where the theorem applies. Last of all, because we've established this for all finite fields, we can union up all this information, stitch it together, and then we can also describe the module structure of all points defined over the algebraic closure as a module over the endomorphism ring of FQ rational endomorphisms. So this again is just stitching together the stuff that we've seen before. Thanks for listening.